Hello there. In this lesson we're going to continue to look at probability. We're going to learn about something called relative frequency, which is also known as experimental probability. By this point, after the last lesson, you should be quite confident at being able to calculate the probability for a number of events. But sometimes it's very difficult to have enough information. So if you recall, the probability is calculated by how many outcomes there are of what we're interested in. Well, what about applying that to the probability of whether it will rain in Ireland tomorrow? How could we do that? Let's remind ourselves of how we worked out the probability of an event. We take how many there are of what we desire, of what we're interested in. Well, if we were to try to calculate the probability for whether it will rain tomorrow in Ireland, how am I going to find out the number of desired outcomes, the number of times it could rain? Could be quite tricky. We might have to look at some statistics, perhaps from the CSO office, or maybe even look at historical weather reports. But there's another way that we could do it, and that's experimental probability. Experimental probability, or relative frequency, and it appears as relative frequency more often in the Junior Cert exam. It's a rough estimate, so an approximation of the probability of an event. And this is used for when it's quite tricky to use theoretical probability. So we're going to conduct an experiment. We're going to actually look at the patterns of weather and record on many days whether it rains that day or does not. So that means I'm going to make lots of trials. Rather than looking at the theoretical probability, we're actually going to work it out. And I can look back on the historical records, so our accounts of how many days it did rain over the period of time that we conducted the experiment, to then predict the next day. What is the probability then that it might rain again the very next day based on our historical records? Your first letter to write down is the letter L. Okay, so to do this then, to look at the estimated probability of it raining tomorrow in Ireland, then I would need to create something like a frequency table. Now, a frequency table is something that you will have to learn as part of the Junior Cert, and you'll come across many times, especially when we start to look more at the chapter about statistics. Frequency is an important keyword, and it means how many. So we're going to be creating a table to help us figure out how many days did it actually rain and how many days did it not rain. So each day we would open up the curtains and we would look outside and then determine, has it rained that day or has it not? And we would put what we call a tally underneath the correct title. Now, a tally is simply a little score. It's a little line down like this. So the very first day, it rained, and I put a little mark. The very next day, it did not rain, so I'm going to put a mark in this column. The next day, it rained again, and it also rained again. And it rained again, and let's have a look. Oh, it rained again. So when we get to the fifth tally, rather than writing another line down, we're going to make it really easy for ourselves to count, and we put a diagonal across the previous four. Now, what this creates is like a gate, and gates make it really easy to be able to count how many there are. Every time we have this gate, we know it's a set of fives, and counting in fives is quite easy. Okay, so far we have conducted 6 trials On 6 days, we recorded whether it rained or didn't rain. So, do you think, looking at the 6 trials that I have recorded down, that I would have a really good ability to know whether it's going to rain the next day? Perhaps not. Maybe we didn't look at as many days as we should. And that's a really important fact, that the relative frequency, experimental probability, the estimate of probability, is only really accurate if we perform many trials. So rather than looking at just what happens over 6 days, that I would look at 100 days or even more, that I would look at the entire year, 365 days. Then it would be a much more accurate estimate of the probability of whether it will rain or not the next day. Okay, so if there are a large number of trials, then the relative frequency, our estimate, of the probability will be quite good. So let's have a look at what the actual formula to find our probability in terms of the fraction, the decimal or the percentage that we know is required to describe probability with. Okay, the relative frequency is, and here we have our fraction format again, but on the top of the fraction then this time for the numerator, it is the number of times the event happens in a trial. Okay, so this means how many times did it actually rain? And then on the bottom number is the number of trials that you performed. So it's how many times it did rain out of how many days that we looked at. Well, that makes sense. It's a kind of proportion of how many times it did rain out of the total, and therefore that same proportion should be, moving forward in the future, that should be the same too. So we'd better conduct a lot more trials if we want to have a really good estimate of our probability. Rain, more rain, sun, sunny day. Okay, so it's been many days later and therefore many more trials since. Let's have a look and see what do we do next. So we have our tallies here, and we remember that each gate set of 5 can be quite easily counted up there. Now what we would need to do then is, once we've finished all our trials, is to then calculate the total. So to add up all of our tallies for each of the 2 categories. Okay, so 5, 10, 15, 20, 25, 30, 35, and then I have 2 extra. So that makes 37 trials for days when it rained. And let's have a look when it didn't rain. 5, 10, 15, 20, 25, 30, 31 days it didn't rain. Okay, so now it's time to work out the estimated probability. So let's remember our formula. The relative frequency, so the estimated probability, is the number of times that the event occurred over the number of trials that we did. Okay, so our relative frequency then, which we know is our estimate for the probability, will be how many times that it rained over how many trials there were, so how many days that we looked at. Okay, well, how many times it rained is our total here. So that was 37. And then for our denominator, how many days we looked at, well, 37 days rained and 31 days didn't. So together, the 2 of them will make our total number of trials. So 30 plus 30 is 60, 67, 68. So 37 out of the 68 trials were days that it rained. Now don't forget that we must always cancel down a fraction if we can. However, this one we can't. There is no number that we can divide both 37 and 68 by. So there we have it. According to our experiment, the estimated probability of whether it will rain or not tomorrow in Ireland is 37/68. Now, of course, our number of trials was just 68, which means that that's definitely not 100% accurate. The more days that we would have looked at, the more trials in our experiment, then this figure would be more accurate. But it's a good estimation, a rough, approximate idea. Please pause the video and record the following formula for relative frequency into your notes copy. Your second letter to write down is the letter N. Okay, let's have a look at some worked examples in your textbook on page 128, please. First of all, worked example 8.11. A survey shows that 80 out of 100 people own a car. Find the relative frequency of a person owning a car. So the first thing that we would do in an exam would be to write down the formula for finding relative frequency, and that shows the examiner that we know what is required for this type of question, and even if all the calculations went wrong later on, we would get some attempt marks for knowing the correct formula. Okay, now let's have a look. What we mean is there are 100 trials, and each trial was asking the question to a person, do they own a car or not? And 80 of them said yes. So the relative frequency then would be the number of people who owned a car, how many that we actually discovered or of what we're interested in, out of the total number of people that we asked in the survey, the total number of trials. So that's 80 out of the 100, which of course we would cancel down to 4/5. As a decimal, it could be written as 0.8 or as a percentage, 80%. So we can say that the estimated probability that the next person we speak to has a car is 80%. Worked example 8.12. A hurling team has won 12 out of 25 in their season so far. Estimate the experimental probability. So you'll notice in this question, it uses experimental probability, and in the previous one, relative frequency. So we need to know both names. Estimate, and we're told to give our answer as a decimal this time. So I would have underlined that when I was doing the question myself to make sure that I give my answer in the correct format. So estimate the experimental probability that they will win their next game. So after writing down your formula, we apply it to this particular question. So how many times they did win when we have we've conducted the experiment, we've got actual information from trials that we did. So there were 25 trials, 25 games, 12 of them they actually won. So 12 out of the 25. And to turn it into a decimal then, we would simply divide 12 divided by 25. 0.48. Your third letter to write down is H. This is a slightly more tricky example. An experiment is conducted to show how the number of trials improves the accuracy of the relative frequency. So we've already discussed that the more trials that we do, the more amount of information that in our experiment, the more likely that our probability is a good estimation. And this example will demonstrate that. Michelle flips a coin, and each time she flips it, she records what she gets, whether she gets a heads or a tails. And for each 10 flips, she'll write down her results from that previous 10 of what she had for each. So her first 10 flips, she got 6 heads, 4 tails. So she probably did a tally to help her get those totals. Now, if we just left the number of trials at 10, then the relative frequencies, so 6 out of the 10, 0.6, 4 out of the 10, 0.4. Now, we know the theoretical probability of flipping a coin is actually 0.5. There are one head, one tail, so 1 in 2 chances. It's a even chance likelihood, or 50% 0.5 probability. Now you'll see that neither of these figures is 0.5, which is what they should be, the exact probability. And this shows that, well, we need to do more trials. So instead of 10 flips, let's have a look. She goes on to 20 flips. So if she did 20 flips, then she'd have got 13 heads, 7 tails. Let's have a look at her relative frequency this time, 0.65, 0.35. It's still not at the 0.5 that we know it to actually be. The number of trials is still too low. What if she flipped it 30 times? 13 were heads, 17 were tails. The relative frequencies are starting to be a little bit closer to the 0.5 that we expect them to be. 40 flips. Closer again. Remember that we know the actual probability is 0.5. 0.45 and 0.55 are much closer than the previous relative frequencies. What about increasing the number of trials again to 50? And this time we get 0.48 and 0.52, much closer. Let's have a look at plotting those results on a graph. Well, when she did 10, we got an estimated probability, a relative frequency of 0.4, 20, 0.35, 30, 0.57, and this is just looking at tails at one of them, and then at 50, 0.52. Now we know that the actual probability is this blue line here, 0.5. Notice how far away they are at the beginning when we have a small number of trials, but then the results get closer and closer to the actual probability. And this is true for all experimental probability actions. The more trials, if we continued again, rather than 50, to do up to 100, then it is much more likely that the estimate probability would be very close then to the actual probability of 0.5. So before I get you to perform some of your own relative frequencies and do some exercise work, I'm going to do one question from exercise 8.4 myself. It says the results of tennis matches played by 3 children are shown in the table. So we've got 3 different children, how many games they won, how many games they lost, and how many games then there were in total. Part A asks us, what is the relative frequency of a win for each child? Okay, so when doing my work, like always, I make sure I have a full heading, my page number, exercise number, and question numbers, my date. And for this question, I'm going to be using a formula for relative frequency. So that's my very first thing that I'm going to do, is make sure that I write down the formula as we always would when one is being used. Okay, so that's the number of wins then over the number of games, and we'll have to do that for each person. So for Mia, if we look, she won 4 out of 4. So 4 out of 4, which of course is the number 1, one whole number. So the relative frequency for Mia is 1. So it suggests from our experiment that it's certain that she might win the next match. Again, we only had 4 trials though, so this isn't very, very accurate. Let's have a look at Alex. He won 3 out of 4 games. So 3 out of 4, 3/4, which is 0.75. Now we know that probability is absolutely perfectly acceptable as a fraction, a decimal, or a percentage. But when we look at relative frequency, it is most common that answers would be given as a decimal. Okay, let's look at Sean. So he won 8 out of 12 games. So more trials for Sean. So his estimated probability will be a little bit more accurate than Mia's and Alex, who only had 4 trials. Now 8 twelfths can be cancelled down. We can divide both the numerator and the denominator by 4, and we end up with 2/3. Now that as a decimal is a recurring decimal, which if you remember means it doesn't terminate, it goes on forever. So it's 0.66666666666 all the way to, well, it keeps on going infinitely. So we don't have the time or the energy to write all those sixes, so we're going to put the little dot over the 0.6 to say that we know it goes on and on. So there we have it. The 3 relative frequencies are 1, 0.75, and 0.6 recurring. Okay, so let's look at part B, who says, who according to their relative frequency is the best player? So our relative frequencies, well, let's remind ourselves what this actually means. It's an estimate of the probability that for any of these children to play a game of tennis, that they will win. And we know that probabilities go from 0, which is impossible, to 1, that's certain. And therefore, the number that is closest to 1, well, it is Mia, suggests that it's certain that she's going to win. So therefore, Mia, with the highest relative frequency, is our potentially best player. Now, part C asks, is this a reasonable way of deciding who is the best player? And explain your answer. Well, I think the answer is no. And the reason for that is there are simply not enough trials. Only looking at 4 games for Mia, well, they may have been her 4 lucky days. Perhaps she would lose the next 4. I therefore think that in order for us to accurately judge each of these children, they would firstly need to have the same number of games played to make it fair, as Sean was judged on 12, not just on 4. But they would all have to have many more trials. We'd have to look at much more of their results to have a really good understanding of how good they are. We might write that down like this. No, the number of trials is too low and not equal for all children. So they need to be fair and have the same number of matches looked at. A more accurate estimate would be obtained after recording 100, for example, game results. For your homework, you have question 1, question 5, and question 6 to do from the same exercise, and also one exercise then from your logbook. Thank you for listening, and I'll see you tomorrow. Just for fun, where does your math teacher, Miss Foley, like to go on vacation? Why, to Times Square, of course.